Hello friends, today we'll discuss about measurement of color, that is basics of colorimeter and spectrophotometer. Spectroscopy is a science deals with interaction of electromagnetic radiation with matter. Spectroscopic technique occupies a key position in biochemical studies and some of them are employed routinely and quite extensively. This technique are extremely useful in characterization of chemical compounds in a sample on the basis of their spectral properties. Electromagnetic radiation is a form of energy which does not require any medium for its transmission. It is made up of two components, an electric field and a magnetic field, which is continuously oscillating in space perpendicular to each other. The direction of propagation of both electric field and magnetic field. Electromagnetic spectrum is the range of all possible frequencies of electromagnetic radiation. The electromagnetic spectrum of an object is a characteristic distribution of electromagnetic radiation emitted or absorbed by that particular object. Color is something which is visible and can be seen with naked eye. Essentially, based on interaction of electromagnetic radiation with matter is a quantum phenomena and is based on absorption of light. Colorimeter and spectrophotometer is widely used technique to measure intensity of a color works based on Beer-Lambert's law. What is Beer-Lambert's law? When a ray of monochromatic light passes through an absorbing media, its intensity decreases exponentially with the increase in concentration and path length of the media. It is a combination of two laws, Beer's and Lambert's law. We'll discuss both the law separately. Beer's law. When a parallel beam of monochromatic light passes through an absorbing media, the amount of light that is absorbed is directly proportional to number of light absorbing molecule or concentration of a media. That is, A is directly proportional to C, where A is absorbance or optical density and C is concentration of light absorbing substance in the medium. Lambert's law. When a beam of monochromatic light passes through an absorbing medium, the amount of light that is absorbed is directly proportional to length of a medium through which light passes. A is directly proportional to L. A is the absorbance or optical density and L is the length of a medium. Since the measurement of light absorption depends both the laws, it is popularly known as Beer-Lambert's law. Hence, A is directly proportional to Cl and A is equal to epsilon Cl, where epsilon is known as extinction coefficient. Also, A is equal to log II upon IT equal to log 100 upon T equal to log 100 minus log T, that is equal to 2 minus log T, where II is a intensity of a incident light and IT is the intensity of transmitted light. Then the ratio of intensity, that is IT upon II, is a transmittance. In the above equation, when concentration is 1 molar, that is 1 mole per liter, and path length of a light is 1 centimeter, epsilon is known as molar extinction coefficient, denoted as EM. SI unit is concentration should be expressed as mole per meter cube and path length is meter. As A is unitless, this would give units of epsilon as mole inverse meter square derived from 1 upon mole per meter cube multiplied by meter. Absorbance is also dependent upon area of illumination by incident radiation. However, more practical unit for epsilon are dm cube per mole per centimeter. Definition of molarity and common use of 1 centimeter path cuvette. Sometimes molar absorbance coefficient are extremely large, and in such cases a more convenient way of expressing value is to quote absorbance of 1 centimeter thick sample of 1% solution of the absorbent. This is distinguished by writing coefficient as a A. Now we'll discuss about what are the limitations of Beer-Lambert's law. There are different points which holds for limitations of Beer-Lambert's law. First is, light must be narrow wavelength range and preferably monochromatic. Second, according to Beer-Lambert's law, relationship between concentration and absorbance should be linear, which is achieved only up to particular concentration of solution, that is threshold concentration. Above the threshold concentration, ionic species will interact with each other and absorb less light, and actual absorption is less than expected. As a result, light absorption does not follow linearity after reaching threshold concentration. Third point, solution containing acidic or basic groups may associate or dissociate to form acid-base pairs with altered absorption maxima. The absorption of solution will differ from pH and temperature dependent, and deviation will occur. At high concentration, molecules may polymerize or coagulate to give a turbid suspension and thereby affecting the absorption of a solution. Fourth point, the presence of fluorescent molecule in solution may interfere in the final absorbance of solution. As a result, there will be a deviation from actual absorption of the solution. Colorimeter and spectrophotometer are most widely used technique based on Beer-Lambert's law. We'll discuss about both the technique one by one here. Colorimeter. It is a simple device that measures the intensity of a light before and after it has passed through color solution. Colorimeter consists of mainly 6 parts: light source, condensing lens to render a light rays parallel, filter to generate monochromatic light, sample holder, photocell to convert light energy into electrical energy, galvanometer to measure the electrical energy thus generated. As shown in the flow diagram, light from the tungsten lamp emits light of wavelength between 400 to 900 nanometer, passes through slit, condensing lens, filter, and finally emerges as a parallel beam of monochromatic light. The monochromatic light passes through sample solution and the transmitted light falls on the photocell. Photocell converts transmitted light energy into electrical energy, which is amplified and measured by galvanometer. And galvanometer is calibrated to read absorbance or transmittance directly. Now we'll understand two concepts: what is complementary color and what is complementary wavelength. Complementary color, when a colored solution absorbs a light from a specific color of the filter to maximum extent, then that color is said to be complementary color. What is complementary wavelength? Is the wavelength at which colored solution absorbs light maximally at a particular wavelength is known as complementary wavelength of the solution. Complementary color or complementary wavelength is used to estimate the concentration of substance, because at that color or wavelength only given substance absorbs maximally and contribute to high sensitivity to estimation and also less interference from other substances. Table 1 shows complementary color for some colored solution and its complementary wavelength. To estimate for estimation technique, we plot standard curve. Standard curve is a plot of absorbance versus concentration of a solution in range in which Beer-Lambert's law is strictly followed. Table 2 shows some of the widely used colorimetric assays in biochemistry for estimation of inorganic phosphate, amino acid, peptide bond, estimation of phenols or tyrosine, proteins, carbohydrate like reducing sugar, pentose, hexose, glucose, estimation of nucleic acid like alpha, nucleic acid like DNA and RNA, alpha exo acids and other molecules like cholesterol. And it is measured at specific wavelength depending upon the endpoint of the reaction. There are also some of the limitations associated with the colorimeter, and few of them are: colorimeter is less sensitive as wavelength used is in range of wavelength, not monochromatic light, and it cannot be used to scan or determine spectrum of light. Now we'll discuss about another technique which is widely used along with colorimeter to measure the intensity of a light, that is spectrophotometer. Spectrophotometer is based on phenomena of absorption as a function of wavelength in UV visible region, that is 200 to 800 nanometer. Like colorimeter, it works on a principle of Beer-Lambert's law as we discussed earlier. However, in spectrophotometer, measurement is done at a specific wavelength. Hence, it is more sensitive and more advanced and sophisticated instrument than colorimeter. UV-visible spectrophotometer essentially consists of following components, that is source of light, wavelength selector, also known as monochromator, sample container, detector, signal processor and readout, as shown in flow diagram of following flow diagram. We'll discuss about the instrumental components one by one. Source of light. Here we use two types of lamps for emission of UV and visible radiation. It is important that power of radiation source remains stable and do not change abruptly over its wavelength range. For emission of UV light, we use D2 lamp. The molecular excitation of deuterium or hydrogen lamp at low pressure produces continuous UV spectrum. It is based on formation of an excited molecular species which breaks up to give two atomic species and ultraviolet photon, which is shown in following figure. That is, D2 plus electrical energy gives D2, which is at excited state, and that consequently gives D dash plus D double dash plus UV light. Both deuterium and hydrogen lamp emit radiation in the range of 160 to 375 nanometer. Quartz window should be used for UV region because glass absorbs radiation of wavelength less than 350 nanometer, that is UV light. Tungsten filament lamp is commonly used as a source of visible light and in the range of 350 to 2500 nanometer. Tungsten and halogen lamp contain small amount of iodine in quartz envelope, which also contains tungsten filament. Iodine reacts with gaseous tungsten formed by sublimation, producing a volatile compound Wi2. Upon heating filament, molecules of Wi2 decomposes, redepositing tungsten back on the filament. Tungsten and halogen lamp are very efficient and its shelf-life is approximately double that of an ordinary tungsten filament lamp, and their output extends well into ultraviolet light. They are used in many modern spectrophotometers. Now we'll discuss about wavelength selector, which is also known as monochromator. All monochromator essentially contain following components: an entrance slit, a collimating beam lens, dispersing device, usually prism or grating, focusing lens, and exit slit. Polychromatic radiation enters monochromator through entrance slit as a collimated beam and then strikes the dispersing element at an angle. Beam is split into its component wavelength by grating or prism. By moving the dispersing element or exit slit, monochromatic light with particular wavelength leaves the monochromator through the exit slit. Now we'll discuss about how this monochromatic light passes through and where they enter. That is cuvette. The container for sample or reference solution must be transparent to the radiation which will pass through them. Quartz or fused silica cuvettes are used in UV visible spectrophotometer. Silicate glasses can be used for manufacture of cuvette for use between 350 and 2000 nanometer. However, glass cuvettes can be used only in visible region as glass absorbs UV light. Now we'll discuss about different types of detectors used in spectrophotometer. Photomultiplier tube is widely used detector in UV visible spectroscopy. It consists of photoemulsive cathode, a cathode which emits electron when struck by the photon of radiation, several diodes which emit several electrons for each electron striking them, and anode. Photon of a radiation entering the tube strikes the cathode, causing the emission of several electrons. This amplified electron strikes the first diode, which is 90 volt more positive than cathode, causing emission of more electron for each incident electron. These electrons are then accelerated towards second diode to produce more electron which further hits diode 3 and so on. Eventually, electrons are collected at anode. At this point, each original photon produced, that is 10 to the power 6 to 10 to the power 7 electrons, and resulting current is amplified and measured. Photomultipliers are very sensitive to UV and visible radiation. They have fast response times. Intense light damages photomultipliers and they are limited to measuring low power radiation. Linear photodiode array is another widely used detector in UV visible spectrophotometer. It is multi-channel photodetector capable of measuring all elements of beam of dispersed radiation simultaneously. Linear photodiode array comprises many small silicon photodiodes formed on a single silicon chip. They can be 64 to 4196 sensor elements on a chip, the most common being 1024 photodiodes. For each diode, there is also a stronger capacitor and switch. The individual diode capacitor circuit can be sequentially scanned. In use, photodiode array is positioned at the focal plane of the monochromator after the dispersing element such that spectrum falls on diode array. They are useful for recording UV visible absorption spectra of samples that are rapidly passing through sample flow cell such as in an HPLC detector. Another device used is charge coupled device, widely known as CCDs, are similar to diode array detector, but instead of diodes, they consist of an array of photocapacitors. So this about the instrumentation part of UV visible spectrophotometer. Now we'll discuss about applications of spectrophotometer. It is used to estimate the concentration of solution in UV visible region, hence colored as well as colorless solution can be used for the estimation. Because of its higher sensitivity, it is used to estimate extremely small quantities of analyte. It is used to scan analyte to determine absorption maxima of compounds. It offers selectivity in that each compound in solution or reaction mixture can be determined and estimated, provided analytes are non-reactive and the lambda max are specific. Using this instrument, fast reactions and enzyme kinetics of analyte can be studied. Moreover, small volumes can be used for estimation in contrast to colorimetric estimation.